and I was giving a talk 10 minutes ago. You have a class after this?
Yeah, no.
Just
We
a
have a
colloquium, I think.
colloquium. We have a colloquium.
Which time is colloquium?
4 o'clock.
Molecular
Machine learning.
machine learning.
Machine learning and something.
But the time? 4
4
o'clock.
o'clock.
4 o'clock.
But classes are mandatory. Colloquia are not.
Well, we could do 1 hour and we do the rest tomorrow as well. Half an hour tomorrow, if you agree. Or we do today 45 minutes and tomorrow 45 minutes.
When tomorrow? What time?
When are you free?
We only have a class at 4 o'clock.
It will be better because I'm exhausted. I just give a talk of 45 minutes. Give me a second.
Oh,
Professor Maxidi course.
Okay.
Just 15 minutes after the course.
after the course.
Yes.
Yeah, so you can go before, right?
Okay, so we do it before.
Yeah.
He could teach at 2 tomorrow. Is it good?
With us, yeah.
Yes.
Can you back?
Sure.
I think it's better today if you.
No, today I will teach, but there is a colloquium and it's obligatory. You cannot. And until the colloquium, there is 1 hour 15. So I cannot do my full class today. But I can do half today, half tomorrow. Is good? Okay, we do half today from now till 3:30. And tomorrow we can do at 2 to 2:45.
Okay.
Let me add it. Just 1 second. So today's lecture 6, no? 6.5. And I put 2.
Because the things were in Croatia. I just got it. Yeah, sometimes, so when I'm in the postgraduate room, the things.
1 second, Location is room 8. Okay, I think this should be added in your calendar. Okay, looks good. Okay, you're hearing from there, Jonathan, Anna. So hope you're there. Sorry for my delay. I was giving a talk online and I expected to finish earlier, but always in the conference things get delayed, as you could expect. So today, well, first of all, any doubt about what I explained on the last day? Any question? I'm happy to solve the doubts before more doubts come, because this will become a bit more complicated. No?
No, if you describe everything like this, we will have no doubt.
Okay, I'll do my best. I'll do my best. All right. So let's continue and go. Fine. Today is lecture 5. The topic will be also stochastic process. In particular, today I will introduce you to the correlation functions. You know, maybe some of these things you already know. And Markov process.
Excuse me, the previous lecture was lecture 4 or 5?
That's fine.
I remember you said 4.
And etc. Let's see how far I can reach. So, first of all, Let me start by introducing to you an interesting object that is the correlation function. As usual, the best way to introduce your new concept is with an example. So let me consider the following stochastic process. It could be this. Okay? This is a drawing, but this way. And the second stochastic process, which has a different structure, which has correlation. I hope this is useful for you to understand what are the correlations. Imagine you have a process that makes oscillations on average, but it's fluctuating near an oscillation. So it's doing something like this. Okay? Now the question is, how correlated is the value one time, which we could call it time t1, with the value at another time different, which we call t2. We take it here, for example, t1, and here. And now I ask you, how correlated is this process and how correlated is this process? So, briefly, from what you see, is this process highly correlated or not? No. Okay. Why do you think it's not correlated? What do you mean? Okay, correlation is statistical dependency. If I am correlated to you, it means if I am up, you are down.
It is because it's correlated with T.
No.
No?
I'm thinking about correlations. Okay, this is, for example, correlation because of this between x at t1 and x at t2. Not about the times, because the times are indices. Times I can tell you 0 seconds and 7 seconds. I'm talking about the value of the process time t1, this one. This is x t1 with x at t2. So in this process, does this value influence this value?
No.
It doesn't look like, because it looks very random. It looks like in every time step, you pick a random number. Then this should have small, low correlation. Okay, now let's think about here. Are these correlated?
There's this thing, so yes.
I would say yes, because they are moving in this sign. So if you are here at this time, most likely you will be near this value, near where there is this sinusoid, okay? And if you are at this time, you will be close to this point. So there will be correlations in this. So this is an example, an illustration, but now I will define things. No correlations. No correlation and high correlation. This is just illustration. However, for high correlation, we can think about other examples. Another example will be, okay, let me try to do this in physics. In physics will be, you have a harmonic potential, you have a particle, initially, okay, this is 0, this is x, and this is a potential, V of x. You have the particle, you put it here initially. What will happen with this particle? It will fall. But this was classical mechanics. It will go to 0. There will be damping. If there is damping, it will do like this. Starting from here, and with damping, it will do like this. Okay. If there is no damping, you will have an oscillation like this. This is called the underdamped and overdamp oscillation. Okay, these are different oscillators. Now, if there is noise, you won't see these oscillators. You will see oscillators with noise. So if it's overdamped, you will do like this. Okay, something like this. This is also a process with correlations because you see that this time and this time are correlated because you are high. Most likely next you will be lower. But when you are here, if this is T1 and this is T2, here the motion will be random most of the times. So there will be low correlations. This is to tell you that correlation is time dependent. Okay, correlation. In general, time dependent. Right. This is an illustration, but now let me go to the math. How do we define correlations? So this is the object. I call it C of T1, T2. This means the correlation function of the process between its value of time T1, its value of time T2. And this is a mathematical definition, which is what sometimes I write like these things, it means a definition. Sometimes I write like this. But it depends on the style. Some professors are more mathematicians. Okay, let me just write it like this to remind you it's a definition. Okay, this is mainly the following. It will be the value of x at T1 minus its average 1 times the value of x at T2 minus the average value of x. So what we are doing is we are multiplying one number times another number. Okay, and then averaging. Averaging.
Could you describe this again?
Okay, this is the value of x at T1. Okay, T1 was here. Minus the average value of x at T1. The average is calculated doing many trajectories. Okay.
You're considering how it's different from the average trajectory, yes?
Sure, because you have noise now. You have noise. Times the same thing at time T2. Okay, now this is the definition, but there is another way that is maybe more friendly to write this equation, which is the following. You do x1 times this times this, and you go, and what you get is the following. X at T1 times x at T2. This is the first term. Then there will be x average. Okay, let's do all of them. Then there will be the average of x1 times, okay, this is with a minus, the average of x2. Then there will be minus the average of xt1, the average of xt2. And then there will be this time this is with a plus. Plus. xt1. Okay, do you follow me in this? Or no? If not, please let me know. Okay, there are 4 terms because there's a plus b times a plus b. Now you see 2 of them cancel. These 2 are canceling. They are the same thing. And you are left with this correlator, x1, x2, minus x1, right? This is nice.
I just didn't understand where the first term came. The average of xt1 is t.
Okay, this is a plus b.
Yes, yes.
Okay, it comes from this times this.
No, but I want to know why they are both inside the average.
Because this is our definition. Is the average of this product. Okay, there is a big average here. Okay.
The average for the whole. Okay.
Yeah. There's one here. There is one here inside. And there is one here inside.
Yes.
Okay. Now with these colors, I think it's better. But you get left with these two terms. This is okay. I think fine. This is. Let me just write it more explicitly. One average, and here is the multiplication of two averages.
Excuse me, have you started recording?
Yes, I'm recording.
Okay.
In case you have doubts.
Because it's very important and
Yeah, sure.
don't lose any.
Sure. Okay. This is no brackets in quantum mechanics. So this is just statistical averages. X1, X2 minus X1 average times X2 average. Now, what happens if there is independence? If these two variables are independent, this will be zero. This will be zero. Remember, so this, 1 second, this will be, okay. This is definition. And now, if there is independence, remember, independence between variables x and y means that when you do x and y is the integral of dx dy a x times y. This is the definition of the average of x times y. Independence means that p of x, this is the joint probability, can be broken as p of x times p of y. This, I guess, you get in the course of Mateo. Okay, you have this, you come here, and this becomes dx dy, dx dy, x, y. So this means you can break this integral, you can move the x here and the x here. So dx x p of x times dy y p of y. This is average y. So when you have independence, x times y average is x average times y average. This means when you have no correlations, yeah, I get a bit lost with this x, which seems to brackets, but this is an x. Okay, it means if there are no correlations, this equals to this. So this is equal to 0. This is an uncorrelated terms. Uncorrelated. Uncorrelated. So it means that when there are no correlations, like in that process, you will have C. Sometimes we call it tau, which is usually C of t plus tau. Okay, you take one time t1 at t and the other at t plus tau, and you plot the correlation function and function of tau. In that process, you will get 0. Correlation function will be 0. But okay, this will be for A. This will be A. Okay. For other processes, like for example, this one that is decaying, B. This will be something like this. this one. So this will be a measure of correlations. And many processes are very well characterized by this object. For example, Markov process. I think you started with Matteo to discuss this. Markov processes have exponential correlation. Correlation decays exponentially. Okay, just two examples. One is IID process. IID process. The IID process is very simple because you are drawing every number with the same distribution. So it's totally independent. It's totally incorrelated. IID processes C of tau equals to 0 for all tau. Markov processes will have C of tau goes like exponential of minus r tau. It will decay exponential.
What's the Markov process?
This is what I will explain you. I think with Matteo, you started to learn.
I'm here.
You had 1 day of Markov process.
No, I'm here.
With Andrea, he introduced Markov process, but in this lecture, I will introduce you Markov process. Okay. Okay. Start coming soon. Okay.
Thank you. I wanted to just ask you, please do not consider anything that you studied before.
Well, I have to motivate you, not to learn new things. Okay, these are the most studied stochastic process of all, Markov process. Please?
Yes. And that means if we can predict a future point or a future position, knowing the present position, the system is correlated.
Yes, yes. You can predict in a sense there is a statistical dependency. In this case, you can predict something when the correlation function is positive. This correlation function is positive. Okay? In this case, you cannot predict anything. It's just random. So if it's IID, you flip a coin today, you flip a coin tomorrow, you cannot predict nothing about the flipping of the coin tomorrow. You can't, because there's no correlation. Okay? But in other processes, you can predict. For example, you put a ball in a fluid, there's turbulent flow, so there's motion that you are pushing the ball very far. You can predict if it has a lot of acceleration, it will continue going. Like a running particle, you can predict things. When you drift it, you can predict. This is Markov process. If it's a coin, I don't care what you happen with your coin today. What will happen tomorrow, there's no correlation. Unless it's a magic code, okay? You know something about it. Unless, okay. But this is the idea. Prediction in a way. All right. And you will see it very clear in the Markov process why there is wrong. All right. This again is for 1D, X. There's only X, but one can generalize for many dimensions. So this is what we call in physics generalization. And greater than 1 dimension. 1 dimensions or different times. So one could do different times. But okay, by now, let me just keep with it simple. N greater than 1 dimensions means you have stochastic process that moves in 2D or 3D. So one example, you move in XY and you have this process. Or another, you move in XYZ and you have this. Okay. Okay. This process could have correlations not only in the 3 axes. In principle, there should be correlations in 3 axes. But you could, for instance, have a motion in a cylinder in a way that the Z axis doesn't have any correlation with X and Y. It will strongly depend on the geometry and the physics of the system you look. we can generalize the correlation function to any dimensions, and this we can call it like this, sin you know, defined as move minus 1. Okay. Here, mu and nu are different dimensions. Or it could be also, not only dimensions, it could be particles. You could have, this is one example of different indices, but you could have also motion in 1D. This is the real line X, and there are 3 particles. Particle 1, particle 2, and particle 3. And imagine you put a spring between 2 and 3, and 1 is free. So in this example, 2 and 3 will be correlated, but 1 will be uncorrelated to the others. Okay, so let's say generalization to n plus 1. Okay, it could be many things. Just to give you an example, if you have one particle in 3D, you could think about C Z 1, 2. This will be the correlations between the variable x and the variable z. So it will be x at time t1 times z at time t2 minus t1 z t2. One example. The other example is the one I say here. 3 particles in 1D. So in this case, I could say C of x1 and x3, for example. T1, T2. This will be x1, T1, T2 minus x1, T1, x3, T2. You can build infinite examples in this way. So, I don't have much space, but I need to write something at the bottom to finish this part. Now you are going fast writing, so I think I can take out this part just to show you.
Here, you describe the correlation between the variable x and z, and below you show the correlation between x and x3.
Yeah, these are 2 different cases. Here, I have one particle in 3D, so I take 2 dimensions, and I look at the correlations of the 2 dimensions.
Okay.
In the second example, I have 3 particles in 1D. This is equivalent to 3 dimensions, because you can map these dynamics in a cube, in a 3D. Okay, so it's the same story. Even more complicated would be n particles in n dimensions, and then it will be bigger. But as you see, what happens now is there are these 2 indices, and you could think about this as a matrix. A matrix has 2 indices, the row and the column. So you could write this as, and you could find it in many books, as a correlation matrix. Correlation matrix. How does this come? Of course, the matrix, the size of the matrix will depend on how many particles we have and how many degrees of freedom. So correlation matrix could be 1 by 1 matrix, like here. Could be 2 by 2 matrix, like here. Because here it's correlation x with x, y with y, and x with y. Here it's even worse. It's 3. 3 times 3. X with x, x with z, x with y with x, y with z, y. So I give you an example. Okay, example for one particle in 3D. This will be a 3 by 3 matrix. We write it like this in bold. C of T1 will be a 3 by 3 matrix, which will have T11, T1, T2. This is correlation of X with X. Actually, you can arrange it in many ways. T12, correlation X with Y. C13, T1, 2. Then C21, C21, C12, C2, C3, 1, 2, sorry, 1, 2, 1, 3, 2, 2, 2, 2, 3, 3, 3. This is the idea. So this builds correlation matrix with each element given by the correlation of each variable with another one. Here this is with X. I could call this XX as well. Y with X, which is X with Y. Not always will be symmetric. Okay, not always. Depends on the process. Most physical examples are symmetrical. Not all of them are symmetrical. This is an important point of physics. Okay.
Just a moment.
Yes. I'll do a small pause because water.
The previous one, you considered just the particle 1 and 3, yeah?
Mm-hmm.
And now you're writing a matrix for all 3 particles.
I could do the same with this example. This is one particle in 3D, but it could be 3 particles in 1D. But if I have 3 particles in 2D, it will be bigger.
Yeah.
Okay.
And this matrix, this matrix is showing what the correlation is at the end.
This will be.
I mean that I expected something like an operator operating in a vector space and giving the results, but
Yeah.
matrix is an operator.
Matrix is an operator. You could use this as an operator, but by now I'm just telling you.
But of correlation, we must expect a value that
Yeah.
shows us how much they are related.
Sure,
That
sure.
is not a matrix.
Sure. If I give you the dynamics of a process, you will be able to calculate this. Okay. I give you the equations of the model. You will be able to calculate this because you come here and calculate. You will be able to compute. You need to know the distribution of the process. In Brownian motion, you can do it already. You know the distribution. You know X. You can average.
Okay. So if I understand well, you are showing the correlation in time 1 and time 2 of one particle with it's in different times with the matrix. That in each time you have a correlation between x axis and x axis.
Yes. Yes.
And x and y and x and z.
Exactly.
And
these are matrix whose numbers, whose entries will depend on time. It's a dynamic object. Okay.
Yeah. Thank you.
So what's the question?
It's okay.
It's okay. Fine. Good. If this is clear, we can continue, and then I will give you examples of stochastic processes that are quite useful, quite common as well. So there are two that I believe are incredibly very much used in physics. One is Markov process, and the other is the stationary process. And then there is the Markov stationary process. There will be many families come here. So, first of all, I was already introducing you to the Markov process, so I would prefer to define it. I think Andrea told you briefly about it, but I'll give you the most rigorous definition I can give you, so you can have things more clear. So, Markov process. Sometimes are called Markovian as well. Okay. We see in physics papers many times Markovian, non-Markovian. Markov or Markovian. Okay. So these are processes that have correlation, and they obey what is called the Markov property. So what is the Markov property? Property in words is the following. What happens in the next step only depends on your current state. Okay? So it's like, well, I can give you a mathematical definition and then an example, but imagine that you have, I don't know, you know this game, no? Of jumping, when you are kids on this jumping, then jump between different positions. So if you are in one of these places, you can only jump to the adjacent states. This is somehow an illustration of what is a Markov process. Where you can go only depends on where you are. There is nothing, there's no influence on where you were 5 steps ago. There's memory of only one step. This is the main concept. So mathematically, this is defined as follows. The probability to be at time n in Xn, given that you have a previous history, the previous history, I'll call it X1, P1, X2, P2, to X n minus 1, P n minus 1. So, okay, this is the probability to be at time Tn Xn. This is the past history of the process. This is the full past history. Okay. This probability only remembers the last step. So all this is not remembered by the Markov process. The probability to be at time n in Xn, given all the past history, equals the probability to be in Xn Tn, given that at time Tn minus 1, you were at X n minus 2. Okay, this is the crucial sequence. That's the way a Markov process is defined. Okay. So in words, the outcome event only depends on the previous outcome at Tn minus 1. This is valid for all x1, x2, xn, for all. And for all Tn minus 1. It means a Markov process is Markov if I pick the time here and here, but also if I pick the time here and here. Right? Very important. This doesn't appear in many books. But tick versus tick. This is the history. And imagine I know up to Tn minus 1. So I know all this history. What happens next only depends on this time. But if I don't know this time, this is when Tn minus 1 is here. But it could be this Tn. Then there will be Tn minus 2, Tn minus 3. So you can pick the time you want in the Markov process. This property has to be satisfied. This is important. So if Tn minus 1 is here, it could be this, you don't know this. But this was your Tn minus 1, and this was your Tn minus 2. Still you will have to solve it. Okay. Of course, the function will change. This you will see in examples, but you will have this property. This is okay, the full past history, and what I put here is the previous state. Okay. This property has consequences, and the main consequence is that in a Markov process, it will be much easier to calculate full probabilities of full trajectories than in other processes. Okay, I said that in IID process, we have P of x1, T1, and Dn. This is very simple because there are no correlations. P x1, T1, P x2, T2, xn, Tn. Okay, here, don't get troubled by the t's. The t's are indices, and these are random variables. So this is, probably in the course of Mateo, this will be like P of x1 at time T1. T1 is just an index. So this is product of probability. P of T2 at x2, and then P of Tn at xn. Each IID, this distribution doesn't depend on T. So you can also remove this T1, T2. Okay. So it's a product of probabilities. Px1, Px2, Px. This is for IID. Markov process don't obey this equation. They are a bit different. It will be strange because it will be strange that this doesn't appear. Here there's no correlation in the probabilities. Markov process, it should appear P x2 given x1 somewhere, and x3 given x2. This is what I'm trying to prove now. And let's see if I have some space for this. Okay, I think so. So let me compute as an example. So from this implies the following. I'll calculate T x1 T1, comma, x2 T2, comma, x3. What is this? First of all, I will apply Bayes rule here. This is Bayes, which implies that this equals first will be this P x1 T1 2 times P T3 given 1. Oh, with this you can see. What I did here in Bayes rule, I call this A, and I call this B. And I say P, A, comma B, joint probability equals P of A times P of B given A. Okay. Should be simple. Another thing is I call A this event, the joint X1 and X2. This is base. Now, the next step I do is I apply the Markov property, because here you see x3 given x1 and x2. If this process is Markov, I don't care. It's 1. In the second step, let's go here. Second step, I apply the Markov property. So I apply this one. Markov. Means that I keep the first 1 to 1. The second, I said, I don't care what goes x1, I only care what goes x2. P x3, p3, given x2, p2. Okay, I'm almost done. Now what I do is I apply again Bayes to this one. Now this is A and this is B. A joint B, this will be P of A, P of B given A. So this becomes, now I apply here again this. This will be P of x1, 1, then P, x2, P2, given x1, 1, times whatever I had, this one, x3, P3, x2. Right? So, you follow the 3 steps?
And could you please
Repeat.
describe what's going on?
What's
Sorry,
what's going on? Let's describe what's going on. We are it's a stochastic process here, and I have low oxygen. So let's see. I'm trying to calculate in this place the probability that at time t1 I'm here in x1, at time t2 I am here, and at time t3 t3 could be anything. T3 I am, for example, here. So I'm trying to calculate the probability of this path, of one path. Okay.
You're calculating probability of going from T8 to T3.
I'm calculating the probability for this trajectory to occur, the full trajectory.
Full trajectory.
Full
at
trajectory.
once.
Yes. Not only x, not only x2 given x1, the entire trajectory. Because if you know this, you know everything in the process.
Okay. How you can find this trajectory?
Is any trajectory tell you, say, I want to know what is the probability that at time 0 you were in 1 nanometer, at time t2 you were in 5 nanometers, and at time t3 you were in 11 nanometers.
Yeah.
3 numbers I want, whatever. And these are 3 times that I want, whatever. I want to calculate this because this is all in the stochastic process. And my only assumption is it is a Markov process. I just tell you it's a Markov process. And say, okay, if it's a Markov process, things are easier. Why? Because now I'm showing you. So this, first I apply Bayes. A is x1, x2, and B is x3. So I do P of A, it is x1, x2, and P of B given A. So it's P of x3 given x1, x2. Okay, now this is equally difficult because I need to know what is the probability of 3 given the 2 past. But in Markov, it simplifies. I don't care about this. The definition of Markov is the probability of x, here is x3.
We forget everything.
We forget, no, not everything except x2, except the last one. You can, I can put here x11 and put you here up to x10. You shouldn't care about until x extend. This is what I do here. Okay. Sorry. This is what I do here. So from this, this is the Markov property, right? And in the last step, I apply again Bayes. Okay. Follow me? Right? Okay. Reach there.
We used to take notes in English because we had university in Persian and school in Persian.
Yeah, well.
So,
I understand. I was having lectures in Spanish until postdoc. But this is math. This is not English, eh?
English words, and I have to notes. Take notes.
Yeah, sure.
To understand what's going on with the math.
There is also the YouTube video later. So. Okay, I reach here, and now I have another joint probability, and I apply Bayes again. So Px1 and Px2 given x1. Fine. So what you see is that the 3 becomes a one variable probability, Px1, and then conditional and conditional. So it's x1, x2 given x1, and x3 given x2. So it has a very simple structure. It means that to calculate the probability of 3, you just need to know two objects, the probability of x and the 2-time probability, the conditional probability. If you continue, and you could do this for x equal 4, there will be 2 steps more. You could do it for 5, you could do it for 6. What I'm giving you is what happens if you can generalize this and get the following equation. T1 is to T2 up to, okay, let's say x3 T3 up to xn here. Now, this has n steps, which could be even 1 million, whatever. This one, and this becomes just the following P, the initial x1 T1, and then it becomes all of them. A product, 2 given 1, 3 given 2, 4 given 3, n minus 1, exactly. So it goes a product from I equals 1 to n minus 1. There are n minus 1 because here we have 3 and we have 2. With n, there will be n minus 1. So from 1 to n minus 1 of p x I plus 1 p I plus 1 given xi a product of n conditional products. And this is a very important equation for Markov process. Tells you that you can compute any probability of any trajectory knowing only two objects: the distribution and the propagator or the conditional probability. Okay, here, sorry, there's no spaces, n minus 1. Right. And this is often people will tell you what is a Markov process, they will tell you this. Other people, maybe if you look at Andrea's lectures, you will find this equation. Or Mateo's course, it will be this equation. But this is the idea. You compute everything step by step using conditional probabilities. That's the point. And I don't know if I have more time, but I should stop because I told you it's going to be 45 minutes. I better prefer if you have questions, I solve it. The next thing I will do is to discuss stationary Markov process. This is a non-stationary because these probabilities will in general depend on time. There is one type of Markov process where these do not matter. It only depends on the difference of the t's. And this is called stationary Markov process. This I prefer to go slower and explain in the next class, and also give you examples of Markov process. But by now, keep this in mind because this is general definition, and if you know this, you will understand very good my next half lecture. Okay, more questions? From the other side of the world or from the guest house, did you understand? Please, if you have questions, this is a good time to ask.
Do you have examples?
Yeah. Yeah, I can give one example of one example is the random walk. The random walk that I presented to you. Actually, yeah, this I have time for an example. This is a good point. I'll give more in the next class, but one simple example is the random walk that I introduced in the previous lecture. Examples. One example is the discrete time random walk. Okay, so what do you need here? Let's say, what is P? What is this? Remember the random walk. You go to the right or to the left with equal probability.
It's probability of +1.
Yeah, but that's a jump probability. What is this function?
It's probability
Of being in the next place, conditioning
Yeah.
to having in the previous.
So there should be a connection. There should be a way of saying from x1, I can only go to x1 plus 1 and to x1 minus 1. There should be a function I can write here that connects me one to another. And this function is the Kronecker delta. The Kronecker delta is, okay, 1, Kronecker delta ij. 1, when I equals to j.
It could also be the indicator.
Yes, sure, the indicator function, but let me try to do is equal to this. 1/2 of delta. Okay, we can do it in many ways, but the way we can say is that x2 should be x1 plus 1 or x1 minus 1. 1 plus 1/2 delta of x2, x1 minus 1. That's it. This is a one line, the random book. One line. This is that. Okay, you see it now because this is only 1 when x1 plus 1 equals x2. And this is only 1 when x2 is equal to x1 plus 1. That's it. And that's the Kronecker delta. I could also, as I said, you need two objects. The conditional probability and the one-time probability. Sorry, one-time probability, the conditional probability. Yes. So this is the, there are two objects. One is the one-time probability density, PDF, and 2 is the conditional probability. Conditional. Two objects. That's all you need. So the density in the Markov process is.
You're continuing.
Huh?
You're continuing.
No, I just have one line more. Okay. But let me just give you the result and we discuss in the next. It's just one line. You wanted more?
No.
Now you complain.
I want to just focus on this concept.
Yes. Let me just give you what is PXT, and then okay, this will take me. Okay, I think probably it's better in the next class because this is related to the binomial distribution and I prefer to go slow. It's related to the binomial distribution. I can give you the result and we discuss. PXT is 1/2 plus 1/2 n minus t divided by n plus. This is the binomial distribution. So I can give you a result and you think about it. N plus is the number of jumps to the right, and n minus the number of jumps to the left. This you can compute. It becomes, you can give a try. If you can prove this, this is equal to this. P plus x half factorial P minus x half factorial. Okay, this is PXT. I'm going to give you this as an exercise to try at home. This won't be part of the official homework, but try to solve this on your own. And it's a good exercise to you to connect with the other course in probability theory. Okay, try to calculate this on your own, and you tell me tomorrow if it's PXT.
Here you write
Exercise.
No, one down here, 1 and 2.
One time probability density function,
Yeah.
which is this P, and the conditional probability, which is this P, x given y.
Okay.
These are the two only things you need to know to fully determine a Markov process. So if I know these two, I could compute everything
Okay.
in terms of probabilities of trajectories.
Okay. And now this probability is
This is for one example. This is
the down. It's discrete.
discrete time and discrete space.
No, I mean that what was binomial distribution.
It's binomial because it's if you want to be at x times t, there are many ways to go there. This is what I want you to think about it. Think about this calculation.
Okay.
What is the probability in a random walk that you are at time t in x? How many paths there exist that reach there? Because you could do 3 steps to the right and 1 to the left, or first 1 to the left, and then 3 to the right.
Just before this lecture, me and Edis were talking about this subject outside for about an hour.
There have been centuries, but decades of research on this, so it makes sense. I do research on these topics as well. We can be months talking about this. I'm just trying to simplify things. Okay, so we stop here, and tomorrow we do the second half.
We start at what time?
At 2. Tomorrow there's no conference. I won't have a delay, so I will be on time. Okay. Thank you.
You want to go to